Here we go, calculus snobs. We're ready for example number 3 underneath related rates. So again, get out your notes and get out your examples if you would. And hopefully you're getting in the habit of reading the questions before you watch the video. But anyway, example number 3 talks about gravel being dumped from a conveyor belt in such a way that it's forming a cone. All right, so the idea would be here's this conveyor belt and it's dumping this gravel on top of this cone. And so if you think about it, as that gravel continues to be dumped onto the conveyor belt, the volume of this cone is changing, as well as the radius and the height. Again, I put those dimensions on there. Those would be the characteristics that would completely describe a cone, would be the radius and the height. All right, given the fact that there's a cone involved in this question, I think we should maybe get a little more excited about this. So you might have to ask your parents about this, I'm not sure, but perhaps you're familiar with the cone heads, and if not, maybe I'm so old, maybe you'll have to ask your grandparents, I don't know. But anyway, so we're talking about a cone, and it would be described with its radius and its height. So as we mentioned before, we're going to need to write some sort of formula or equation that would be relevant to this question. It talks about the volume of the cone. So once again, you would need to look up, or hopefully it's in your noggin, you would be able to pull out what the volume of a cone is. You have the entire Google machine available to you if you have to do that. But anyway, you would discover that the volume of a cone is 1/3 pi r squared h. Again, you can look these things up, they're in books, they're on Google, do whatever you need to do, but that would be the formula for the volume of a cone, since this described the volume of a cone. And I'm sure many of you are wondering about if I'm going to use the cone head voice. I wonder if you're familiar with it at all. And maybe we'll drop that in periodically. But anyway, going back to the question, and the thing is, we also talk about the fact that once we get our equation set up, we want to figure out what rate we want to find. I think since there's 3 variables here, there'd be 3 potential rates they could ask. What's the change in volume with respect to time? What's the change in radius with respect to time? What's the change in height with respect to time? How fast are any of those 3 changing? And I could make a question that would be any of those 3. But if you read the question carefully, you will find, and I would tell you that's usually going to be where the question mark is. It right here says, how fast is the height of the pile increasing? So we want to find the change in height with respect to time, Beldar. All right, so anyway, when it says, how fast is the height changing, that would be called DVDT, the change in height with respect to time. Did you get that? Anybody have any questions? Sorry, Mr. Soybean here, Mr. Conehead is having trouble hearing. I don't hear any questions, so I guess we'll go ahead. So we're going to find the change in height with respect to time. Now, this question has a characteristic of peculiarity, if there's anybody who knows anything about peculiarity. But anyway, sometimes, and this is the first example we've seen where this happens, the fewer variables, the better. We could go ahead and differentiate this thing. And I wanted to point out if we did so, we would actually be using the product rule here, because this is a quantity with one variable being multiplied with another variable. And that would indeed be the product rule. But if we read the question carefully, we'll be able to simplify things a little bit, because it says right here in the middle of the narrative that the diameter, the base diameter, and the height are always equal. And that's a secondary relationship we're given. Now, not all of these will have a secondary relationship, but if they do, you should take advantage of that. So the point of that would be the diameter, as you hopefully know, would be, instead of halfway across that circle, it would be all the way across the diameter. And so that diameter, if you think about it, would be twice the radius. And it says that that diameter, twice the radius, and the height are always equal. So if you're given a secondary relationship involving these variables, it's a good idea to take advantage of that. Honestly, I don't know on your homework if this will happen on any of your questions, but if there is something like that, do take advantage. Now here's the thing though that's a little bit tricky about this. Since this secondary relationship is already solved for h, it seems it would stand to reason that we would take that 2r and put it in over here for h. But the problem with that is that if we did so, then we would no longer have h in our equation, and we couldn't find dHdt. We could, but we don't want to go there. Just trust me. All right. So the point of that is, even though it seems counterintuitive, we actually need to solve this for r and substitute for r in that original. Some people would disagree with this, but you know, whatever. And I can totally understand why somebody might disagree with somebody who looks like this. But you know what? Nobody's here to argue with me, so I'm just going to do what I'm going to do. All right, so anyway, r turns out to equal h divided by 2. And like we've seen in previous episodes of calculus, we can now take that expression that's equal to r and come back over here to our primary, our beginning one, and make that substitution. And that way we'll get rid of a variable, and that will simplify things quite a bit. So, upon making that substitution, again replacing r with the expression h over 2, remember the squared, it's just part of the formula. All right, so there we go, we make that substitution. Let's do a little bit of algebraic simplification. So we do a little bit of algebraic simplification here, and we've discovered that v equals, and I understand I'm maybe doing several steps at once, but this is calculus, and as we've said many times, it's just algebra. So anyway, because of the fact there's division here, we can drop the squared on both of those. And if you do a little bit of cleanup on that, let's take care of the number first. When you square that 2 down there, that'd be a 4. You could then go ahead and associate that 4 with the 3 clear out here. So it looks to me like numerically, this would be a 1/12, 2 squared 4 times 3, 1/12 pi, and when you drop the squared on the h, that becomes h squared times the other h that's in the formula, h cubed. Yay, one variable on that side of the equation. So rather than having to do the product rule, rather than getting to do the product rule, we're down to just a single variable. So anyway, that will indeed make it much simpler for us to be able to differentiate with respect to time. So, now why are we doing that? Right here, we want to find dHdt. Ow! All right, so anyway, hey, put that down over there, pay attention. So anyway, if we differentiate both sides with respect to t, as we've seen on previous examples, this side simply becomes dVdt. This is to be thought of, in my opinion, as a coefficient times a variable to a power. And again, for emphasis, I've learned it helps if we put that in parentheses. It makes people think, again, of doing the chain rule here. So if we start with that external power, all right, you bring that 3 down and multiply it by the 1/12 pi, 3/12. I could write 3/12, but I just can't. That's 1/4. 1/4 pi h squared, and again, that would be the application of the power rule because that's outside the parentheses, so to speak. And then when you go inside, chain, 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 and do the derivative of what's inside, that would be dHdt. Because again, if you differentiate the variable h with respect to t, that's why that's so important, then you get that expression dHdt. So now we're at the point where we can go back and read the question and find numbers and solve for the unknown. So once again, let's identify the fact that we're looking for dHdt. That'll remain a variable, and everything else over here better be replaced with a number in some way. And the information will be provided to where you'll always be able to do that. So, gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. Well look, cubic feet would be a volume per minute. Isn't that the change in volume with respect to time? So 30 cubic feet per minute, change in volume with respect to time, cubic feet per minute. That'll go in for dVdt. Another thing I always emphasize, when you put a number in for a rate of change, ask yourself, is that characteristic increasing or decreasing? Well, since they're dumping more gravel onto this pile, that volume is increasing. So that would indeed be a positive number. It's hard for me to conceptualize, but I'll make it up. Suppose there was this huge vacuum up here that was pulling the gravel off the pile, and it was shrinking. Well, okay, then that would be a negative 30 cubic feet per whatever it was, minute. All right. Anyway, so we've got that. We keep reading, and it says, how fast is that height changing? That's the DHDT. When the pile is 10 feet high. So again, this would be the instant where we press pause on the video of this thing, and we go, at that instant when the height is 10, at that instant, right, snap. All right, so we'll put 10 in for H, and then again, DHDT remains our variable. Apologies for having to transfer this up over here, but I think you'll be able to follow it. So if we continue, again, we've got our 30 over here. I'll do a little bit of arithmetic cleanup. Over on the other side, 10 squared is 100. 100 times a fourth, 25 pi is what this side becomes. So then the equation becomes that. This is just algebra, all right? And then, of course, solving for DHDT, divide by the 25 pi. Now, I will caution you when you put this in your calculator to crunch out the decimal approximation to this, make sure you put that 25 pi in parentheses when you do so. We've had that discussion many times. So again, this part is just arithmetic and just sticking it in the calculator. And again, it'll serve me right now that it's on tape for people to see forever and ever that I mess up, and then you can make fun of me forever and ever. But oh well, what else are you gonna do? Anyway, we're all doing the best we can. I hope I put this in correctly. It looks like this is 0.38197. How many decimals did I keep, Mr. Sauerkraut? I don't know. I don't have a good idea for that. Just do your best. We're all gonna be gracious with each other. For some reason, I went to 5 decimal places. And then the units. Height is a length. Those are expressed in feet in this question. So it looks like the height would be in feet. And then time, minutes, hours, days, eons, centuries, whatever it might be. But it talks about, where is time mentioned? Minutes. All right, so that many feet per minute. And there you go. So, that would be how you would do a question involving a cone, perhaps. I don't know if I gave you one for homework, but anyway, let's all go now eat mass quantities of chicken embryos. See you next.